Hello everyone. So this is a question from JEE Mains 2026-28 Jan evening. A volume of X ml of 5 molar sodium hydrogen carbonate solution mixed with 10 ml of 2 molar carbonic acid solution to make an electrolytic buffer. If the same buffer was used in the following electrochemical cell to record a cell potential of 235.3 millivolts, then the value of X, that is the volume of sodium hydrogen carbonate, that is what we are supposed to find. And a cell representation is given to us. And consider up to one place, this is important, one place of decimal for intermediate calculations. Okay, so we have to just take care of one decimal place in whenever we do calculations in between, and some values of, for example, E naught of the half cells are given to us, both the half cells. pK of carbonic acid is given to us. The value of 2.303 RT by F is given to us, and anti-log of 1.29 is given to us. Okay, so this involves the chapter ionic equilibrium, electrochemistry, redox reactions. Okay, so to start with, first we need to know what is a buffer solution. So a buffer solution is a solution which resists any change in its pH. Okay, buffer solution resist any change in its pH even when we add small amounts of acid or base to it. Okay, so it is a solution, a kind of solution which resists any change in its pH even when we add small amounts of acid or base to it. Okay, so there are two types of buffer solutions. Okay, two types of buffer solutions. First one is solution of single substances. That is, for example, a solution of salt of weak acid and a weak base. Okay, for example, CH3COONH4, ammonium acetate. Okay, so the solution of this salt will act as a buffer. Okay, so we can see this is a salt of weak acid CH3COOH and the weak base NH4OH. So therefore this will act as a buffer solution. The solution of ammonium acetate will act as a buffer solution. Okay, the second category is solution of mixtures. Okay, the above one is just a single substance, that is solution of salt of weak acid and a weak base. The next step we are going to learn is solution of mixtures, which can be of two types again further. Acid, the first category under this is an acidic buffer. So acidic buffer will consist of, so it is a solution of mixture, right? So it will consist of solution of weak acid and salt of this weak acid with a strong base. Okay, for example, CH3COOH, acetic acid, plus CH3COONA, sodium acetate. Okay, so the second category is a solution of mixture, and this further consists of two types. Under this, the first is acidic buffer. Acidic buffer consists of solution of a weak acid, for example CH3COOH, and salt of this weak acid with a strong base. So you can see this is a salt of CH3COOH with a strong base NaOH. Okay, this is a salt of CH3COOH plus NaOH, right? So these two are a mixture and they will form a acidic buffer. Okay. Similarly, we have something called basic buffer also. Okay, so a basic buffer is a solution of mixture of weak base and salt of this weak base with a strong acid. Okay, for example, NH4OH plus NH4Cl. Okay, so a basic buffer is a solution of mixture of weak base. Okay, for example, NH4OH, ammonium hydroxide, is a weak base, and salt of this weak base with a strong acid. So this guy is a salt, okay, of this weak base and a strong acid HCl, right? So this guy is a salt of weak base NH4OH and strong acid HCl. Okay, so these are the three types of buffer solutions that we can have. In the question, we have been given a mixture of NaHCO3. Okay, so in the question, we have a mixture of NaHCO3 and H2CO3. Okay, and this is clearly an acidic buffer because this guy is a weak acid and this is the salt of weak acid, that is H2CO3, with a strong base NaOH, right? So this is salt of weak acid with strong base. So therefore this will form a acidic buffer. So this is a acidic buffer mixture. Okay, cool. So therefore we can use the Henderson-Hasselbalch equation, okay, which is pH is equal to pKa plus log of concentration of salt divided by acid. Okay, so this equation is known as Henderson-Hasselbalch equation. Okay, so in this equation we know few terms, that is we know what is okay, so let us say the volume of the salt. Let us see what is given to us. If you see the question, X ml of NaHCO3 and 10 ml of H2CO3. Okay, so let us write these things down. X ml of NaHCO3 and 10 ml of X ml and 10 ml. Okay, cool. So let us say that when we mix them, that is when we mix NaHCO3 and H2CO3, so let us say the total volume of solution after mixing. So that will be obviously 10 plus X because we are mixing them together. So it will be 10 plus X ml, right? So next we have to let's calculate number of moles of salt. So number of moles of salt will be, we know, right, molarity is number of moles divided by volume of solution in liters. So number of moles of salt will be molarity of the salt into volume of the solution, solution in liters. So molarity of the salt is given to us, it is 5 and 5 molar, and the volume of the solution we just volume of the salt, that is X by 1000, right? So number of moles of salt will be 5 into X by 1000, so which is X by 200. Okay, so similarly let's calculate number of moles of acid. So number of moles of acid will be, so molarity of the acid is 2 molar and volume of the acid given to us is 10 ml, so it will be 2 into 10 by 1000. because we need to convert it into liters. So this will be 1 by 50. Okay. So we know number of moles of salt, we know number of moles of acid. Okay. We also know the pKa of H2CO3, which is 6.11. So therefore, substituting few values in the Henderson-Hasselbalch equation, that is pH is equal to pKa plus log of concentration of salt by concentration of acid. Okay. So pKa is given to us 6.11 plus log of concentration of salt. So concentration is molarity. So molarity is number of moles divided by volume of the solution in liters. Okay, so number of moles of the salt, we calculated x by 200, and let's say the volume of the solution is V, divided by number of moles of acid is 1 by 50 divided by volume of the solution, right? So volume of the solution will be obviously 10 plus x, but I'm not writing it here because anyway it's going to get cancelled. Okay, so when we expand, when we do solve this, so it will be log of x by 200 into 50 by 1. So this will come out to be 6.11 plus log of x by 4, that is pH is equal to 6.11 plus log of x by 4, and our aim is to calculate x, and to calculate x we have to know what is the pH of the buffer solution. And information about the EMF or cell potential of the buffer is given to us. Okay, so the E cell of the electrolytic buffer is given to us as 235.3 into 10 power minus 3 volt. Okay, and we know that E cell is equal to E cathode minus E anode, right? And also we know that for the cell reaction, when we have a cell reaction, that is A moles of A plus B moles of B, which involves n electrons to form X moles of X plus Y moles of Y. When we apply Nernst equation, and in Nernst equation the electrode reaction is written as a reduction reaction. Okay, we have to take care of that whenever you want to write the Nernst equation for individual half cells. So they are written for reduction potentials, reduction reactions. Okay, so when we apply Nernst equation for this, we get one more equation, that is E cell is equal to E naught cell minus RT by NF ln of concentration of X to the power its molar coefficient, stoichiometric coefficient, concentration of Y to the power of its stoichiometric coefficient, divided by concentration of A to the power its stoichiometric coefficient, concentration of B to the power its stoichiometric coefficient. Okay, so this is known as your Nernst equation. Okay, so in this, this is the E cell, this is the standard electrode potential, R is the gas constant, T is the temperature, N is the number of electrons involved, F is the Faraday's constant, Ln is log base E. And when we convert it into ln to log, the equation ultimately changes to E cell is equal to E naught cell minus RT by NF into 2.303 into log of X to the power X, Y to the power Y, divided by A to the power A and B to the power B. Okay, so in this question we have been given two half cells. Okay, so let us say for half cell 1, okay, and let us denote that like this, that SnOH 6 2 minus and HSnO2 minus. Okay, so let us check whether it is reduction potential or oxidation potential, or reduction half cell or oxidation half cell. In this, the oxidation state of tin is 4. In this, the oxidation state of tin is 2. So clearly this is reduction potential. So therefore E naught of this half cell is given to us. So this is E naught of Rp, that is reduction potential of 1, which is given to us as minus 0.9 volt. Yeah. And let us see the cell representation. Let us go back and see the cell representation. So in this, we have been given a representation of a cell, and also we have been given, few concentrations. SnOH6 2 minus is 0.5 molar, HSnO2 minus is 0.05 molar, and also Bi2O3 solid, Bi solid, important, okay? And also this OH minus denotes that, this is happening in a basic medium, okay? So therefore, coming back to, our half cell 1, this is our half cell, that is SnOH6 2 minus is getting converted to HSnO2 minus, okay? So let us write that down. SnOH6 2 minus is getting converted to HSnO2 minus, okay? So in this, we don't know how many electrons are involved, and also this is not balanced, okay? So in case of ionic reaction, so this is ionic reactions, you can clearly see, to balance an ionic equation in a basic medium, so there are a few steps that we need to follow, okay? So the first step is, first balance O atoms by adding H2O molecules to the side which is deficient in O, okay? Balance O atom by adding H2O to side deficient in O. Then H atoms are balanced by adding H2O equal in number of deficiency of H atoms. H atoms balanced by adding H2O equal in number of deficiency of H atom. Third, equal number of OH minus are added to opposite side of the equation. So we have to continue in second, that is H atoms balanced by adding H2O equal in number of deficiency of H atoms, and then equal number. So how the number of H2O that you are adding, okay, in the second step, and the number of OH minus that you are adding to opposite side of the equation should be same, okay? So, and third, an equal number of OH minus added to opposite side of equation. And fourth is, and the last step is, charged, if there is any charge imbalance, so charge is balanced by adding electron, okay? Yeah, so following these rules, let's try to balance this, okay? Let's try to balance this ionic reaction. So they are saying, first balance O atom by adding H2O to side deficient in O. Here we have 6 oxygen, here we have 2 oxygen, so therefore the deficiency of oxygen is in this side, okay? And what's the deficiency here? 6, here we have 2, so therefore 4. So therefore I will add 4 molecules of 4H2O, okay? So let us say this is after following the first step, 4 molecules of H2O, right? Okay, then H atoms balanced by adding H2O, okay? So let us see where is the deficiency of H. So here we have how many H? 6H. Here we have how many H? 8 and plus 9, so 9H. So therefore you can say there is deficiency of H here. What is the deficiency? 3. So H atoms balanced by adding H2O equal in number of deficiency. So what is the deficiency? 9 minus 6, 3. So I will add 3 this side. So plus 3H2O. This is the second step. And third step is an equal number of OH minus added to opposite side of equation. So here I added 3H2O. So I will add equal number of OH minus on opposite side. So this side. So plus 3 OH minus. Okay. So this is the third step, and let us see whether there is any charge imbalance. So here the total amount of charge is 2 minus, here the total amount of charge is -3 minus 1, that is -4. So therefore I will add 2 electrons on this side so that the total charge becomes 4 here. So plus 2 electrons. So final balanced equation is SnOH6 2 minus plus 3H2O, and also we have 3H2O here and we have 4H2O here. So overall we will have 1 H2O on the product side. So I can remove this, so I can write 2 electrons and HSnO2 minus plus H2O plus 3OH minus. So this is the final balanced chemical equation. Okay, so here we had 3H2O, here we have 4H2O. So overall we have 1 H2O on the product side. Okay, so this is the final equation or final half cell reduction equation. So following Nernst equation, we know what is Nernst equation, so we can write Nernst equation for this. So E1, let us say E1, because this is the first half cell 1, so that's why I'm writing it as E1. So E1 is equal to E01 minus RT by number of electrons are 2 into 2.303 log of, okay, so OH minus to the power 3. I am not writing the concentration of water because we assume that it remains constant, and HSNO2 minus the concentration is given to us as 0.05 to the power 1 because stoichiometric coefficient is 1, divided by SnOH6 2 minus concentration is given to us, it's 0.5 to the power 1, right? So this is the Nernst equation, and E01 is given to us as minus 0.9, and also RT by F into 2.303 in the question, they have asked us to take it as 0.059. Okay, so when we do this whole calculation, we ultimately get that E1 is equal to minus 0.9 minus 0.059 by 2 into 3 log of OH minus plus 0.059 by 2. This is what we get. Okay, now going to the second half cell. So for half cell 2, so in the half cell 2, it is represented as Bi2O3, which is solid, forming Bi again solid. Okay, so in this case the oxidation state of Bi is 3. In this, the oxidation state of Bi is 0. So again, reduction potential is given to us. So let us say E0, Rp of 2, second half cell, that is minus 0.44 volt. Yeah. And let's write it down that Bi2O3 is forming Bi. Okay. Obviously, the number of Bi atoms are not balanced, so let's multiply it to form 2 Bi. Okay, good. Now let us see the deficiency of oxygen. Here we have 3O, and obviously there is a deficiency in the product side, so therefore we will add 3 molecules of water, so plus 3H2O. Okay, now let us see the deficiency of H. So here we have 6H, here we have 0H, so therefore we will add 6H2O on this side, that is plus 6H2O, and then equal number of OH minus has to be added. So since we added 6H2O here, equal number of OH minus has to be added on the other side. So this side, we are going to add 6OH minus. So plus 6OH minus. Now let's look into the charge balance. So here we have 0 charge, here we have minus 6. So therefore we'll add 6 electrons here. So therefore plus 6 electron. So overall we can write down this as Bi2O3. So since we have 6 here and 3 there, so 3 on the reactant side. So Bi plus 6 electron plus 3H2O, giving us 2 bismuth plus 6 OH minus. Okay, so when we write the Nernst equation for this, so we can write it as E2 is equal to E02 minus RT by 6 electrons are involved, 6F, into 2.303 log of, you can see bismuth is a solid, so this doesn't come into the picture. So OH minus to the power 6 divided by, in the reactant side you can see Bi2O3 is a solid, doesn't come into the picture. Water, we assume the concentration to be constant, so doesn't come into the picture. So therefore it is just log of OH minus to the power 6. Or we can write it down as minus 0.44 minus 0. So we know this value RT by F into 2.303, that is minus 0.059 by 6 into log of into 6 power, so it will come down log of OH minus, this and this gets cancelled. Okay, so this is the final value for E2. Now we know that E cell is given to us, which is again E cathode minus E anode. Okay, to decide, now we also know what is, we know the half cell values, that is E1 and E2, right? Now we have to decide, you know, E1 is the cathode or the anode. Same thing with E2. E2 is the cathode or anode. For that we need to look into the values of E naught RP, which is given to us. So they have given that E naught of RP of 1 is minus 0.9 and E naught of RP of 2 is given to us as minus 0.44, right? We know that reduction occurs at the electrode having higher reduction potential. Okay, so therefore out of these two, this is the bigger value. So this is where the reduction occurs. So therefore this is the cathode and this is the anode. Okay, so therefore E2 is the cathode since it has a higher reduction potential, and E01 is the anode. Okay, so therefore we can write, therefore that is E cell is equal to, you know, E2 minus E1. Okay, and we know the values of these individual terms. We know what is E2, we have calculated what is E2, we have similarly calculated what is E1 in terms of OH minus. So in this particular equation I can substitute E2 as this, I can substitute E1 as this. Okay, so when we substitute them we get an equation, that is 235.3 into 10 power minus 3 is equal to minus 0.44 minus 0.059 log of OH minus, so this is from this is E2 minus of, let's substitute the value of E1, that is minus 0.9 minus 0.059 by 2 into 3 log of OH minus plus 0.059 by 2. So this is the value of, this is E2 minus, this is the value of E1. Okay, so when we solve this equation we get log of OH minus is equal to minus 6.6. Okay, so and we know that when you put this minus this side, we can write it as minus log of OH minus is equal to 6.6. We know what is minus log of OH minus, that is POH. So POH is equal to 6.6. So POH is 6.6 and we know that pH plus POH is equal to 14, right? So we can calculate the pH here, so that will be 14 minus 6.6, which is 7.4. So now we know the pH of the buffer, that is 7.4, right? Now going back to the Henderson-Hasselbalch equation, which is this, right? Here pH was unknown to us to calculate X, so let us substitute pH as 7.4. So 7.4 will be equal to 6.11 plus log of X by 4. Okay, so I will substitute this value here for calculations. I will write it down again. 7.4 is equal to 6.11 plus log of X by 4. Okay, so when you bring this to the left hand side, we get 1.29 is equal to log of X by 4. And since it is base 10, we can write 10 to the power 1.29 is equal to X by 4. And this is nothing but anti-log of 1.29. And it is given to us as 19.5. So X by 4 is equal to 19.5. So therefore X is equal to 78 ml. So therefore the amount of NaHCO3 solution that we have taken is 78 ml. Okay, thank you.